very much for the invitation to speak to you this afternoon, and it's always a great pleasure to talk to my colleagues in Indonesia and the region. The talk that I'm going to give to you over the next half hour or so, it's a little bit different from all of the others inside this conference, which is looking at battery materials. But battery materials, of course, are inherently non-equilibrium systems. And you're interested in ionic mobility and so forth. You're interested in phase transformations and phase stability. But when we speak about phase stability or phase transformations or defect concentration, what we have to have is a measure against which we're comparing. So what does a low concentration of defects mean? What drives a phase transformation or allows it to happen? And to understand these things very well, there has to be an appreciation of crystal chemistry. And certainly what I've seen over many decades is that crystal chemistry is something of a scary subject to many students beginning in material science, because they're very much interested in properties, they're interested in performance. And so having to step back and think about, why does a material have good or bad performance? Why does a material have order or disorder phenomena? This is sometimes quite challenging. And so what we have done at NTU, and particularly in the School of Material Science and Engineering over the past few years, is really work hard on developing online capacity to teach students both within and outside Singapore, but also to present the information in a way that's more palatable and more meaningful to students. We don't want to turn all students into crystallographers. That's certainly not the point. But we do want to get students to the point where they know what are the correct questions to ask, what are the insights that they need to optimize function, whether it's in battery materials or other functional materials. So what I'd like to take you through very briefly now is the approach that we're taking to EdTech for crystal chemistry and materials chemistry more generally, material science more generally at NTU. And as you can see from this title slide, we take the approach that we don't want to jump directly into crystal chemistry, but basically start with familiar objects like flowers, Peranikan tiling, and so forth, to lead students through the ideas and the concepts that they need to understand crystal chemistry. So I'll divide my presentation into 4 parts, which is, first of all, the drivers. Why do we want to use EdTech and what are the benefits of doing that? The second part, to tell you some of the features of the platform we've developed. This is not the only platform that's available, but it's the one that we use. It's called Atlas, Adaptive Teaching, Learning and Application System. And I'll explain to you how that works. We have to discuss the style of assessment, because I think with online teaching in particular, there are concerns about the quality and the robustness by which we assess students. And finally, the inclusion of some lab practice, because I think we all know that hybrid teaching is often the best, but certainly want to have some hands-on practice there as well. So, of course, we're all emerging from COVID. And whilst COVID was very challenging for many people, there is one thing that did come out of it, which is that we now understand what is possible to do in terms of EdTech. It really accelerated the uptake of EdTech, and I think there was a lot of innovation that took place over the last couple of years. The other thing that I would like to emphasize is that we've been developing EdTech now for about a decade, so much preceding the COVID situation. And providing the EdTech content is designed properly, it is in no way second rate to face-to-face learning. But you can't just take a face-to-face course and put it on a video. Of course, it's much more than that. So if we do things properly, we see that the learning is not only deeper, the learning can be accelerated as well. We can also make better use of peer-to-peer learning, which is a very powerful tool. So the platform, which I'll be showing you a little bit of through this session, the Adaptive Teaching and Learning Application System, or ATLAS, This is something that MSE at NTU has been developing together with Ludwig Maximilius University in Munich, and in particular their spin-off company that has been working on this for many years. So we've been looking at this together with them now for about 5 years. So this is quite a mature system, which initially we used internally in our department, and then we put out as an international system. So what can we do with Atlas, and why do we need to have something like an Atlas or an EdTech approach? The first thing, of course, to say is that learning is much more complicated than it used to be, and the content is more complicated. I think to solve real-world problems, whether they're in material science or elsewhere, you have to really take much more of an interdisciplinary approach, and you also need to have the language of different disciplines to make real progress. So how do we actually present information so that it's more digestible, particularly the novice coming into a particular area? So what we have done is strive in this platform to enable cognitive perception of the major concepts that have to be learned. And what we use, and this little screenshot shows you, but I'll show it more dynamically later, is that we basically divide the landing page in 2 parts. One part is the actual content, which would be typically in PowerPoint presentations, and the other part is a dynamic reasoning graph, because some students want to see what is everything that would be covered in a lecture and what are the connections between the different parts. So as the lecture is playing, the dynamic reasoning graph also is running, and they can see what the progress and the connectivity of the different concepts are. In addition, the nodes that you can see on the right-hand side of the figure, you can attach supplemental information, whether it be scientific papers, additional videos, YouTube content, whatever you want. Because the other thing that's getting very clear, particularly as there are more lifelong learners upskilling and reskilling, is that students come to these courses with very different backgrounds, and there's inevitably some infilling that has to take place. So this is the general approach that we're taking here. These reasoning structures are very important. They're important for the lecturer because it imposes a discipline in terms of how they're going to design the lectures and the content. It also means the students have greater clarity of what will be covered. And finally, of course, students can take a personalized learning path, so they can readily jump between parts of the lectures that they want to look at. So if they're very familiar with one part of the content, they can jump away from that and move to those parts they have to spend more time on. Now, as I mentioned at the beginning, we don't lead ourselves directly into crystal chemistry because when we start to talk about symmetry and we start to talk about space groups and so forth, most students really have no concept of that. So we like to start with something which is more accessible to all students. And some of you who have taught in this area will know that the Escher-style drawings are often a great way to start because they're fascinating and beautiful in their own right. But you can take students through the way in which Escher was able to create these tessellations and how he was very clever at hiding the underlying simple symmetry which was there. And we can create videos like the one that is shown here, where you can introduce on an Escher-style drawing the idea of the repeating unit or the unit cell, which is shown here outlined in purple. And then we can show how objects, not necessarily atoms, but objects be acted on by symmetry to create these intricate tessellations, which are actually no different to what is happening in crystal chemistry, where you put together one or more types of atoms, you apply a certain symmetry to it to arise, to end up with different patterns. And so this is usually something which students enjoy looking at, and it really does allow them to start to understand plane symmetry extremely well, point and plane symmetry extremely well. From that, we then move to something which is a bit more chemical. This is really building upon what many of our students would have from high school, understanding what happens inside an isolated molecule as distinct from a crystal. So we could start with something simple like boron trichloride, and we ask them to help identify intuitively what are the symmetric elements that are there. And of course, most of them can do it. They can see that there are mirror lines there. And then you can have a discussion about what defines the symmetry. And it would be things like the bond angle and the bond length. Again, very simple concepts to begin here. And then what keeps the molecule together? Again, you can talk about electrostatic charges. So, you know, the boron as a cation, the chlorine as an anion. And then we get more to the nitty-gritty after we've gone through what they're familiar with. We say, well, you know, why is this happening? Why do we end up with this triangular symmetry, threefold rotational symmetry in a boron trichloride? So then we start to think about more chemical features, such as the fact that the chlorine ions don't want to be near each other. They're trying to get as far apart from each other because they're negative. We know that there's a nuclear repulsion that takes place as well between the protons. So these are the features that you find in a simple molecule like this. And then, of course, you can extend it to infinite crystals as well. So we can start then to look a little bit more deeply about the general concept of symmetry and how it relates to function of materials. So, of course, we always have to emphasize to the students that crystals and molecules are dynamic. So there's always, what you're looking at when you talk about bond lengths, bond angles is the average, time averaged properties. But more importantly, we know that the boron and chlorine atoms must form a bond. So they have to be as close as possible and to form a stable bond. Then, of course, we've got the chlorines repelling. We've got then a minimum energy solution to this problem, which on average is a 120-degree chlorine boron chlorine angle. And then finally, we end up with the triangular symmetry. But the key thing here is that the students understand what the drivers are. The drivers are the short and strong bonds, and also getting the similar charges apart. The function that we're trying to achieve is the minimum energy solution, and the outcome is the symmetry. So this is very important to understand. The symmetry doesn't drive function. Function drives symmetry. You have to end up with a certain configuration, and fortuitously, as you achieve that functionality, whatever it might be, the symmetry follows, which is often the opposite to how students think about these things. Now, I'll show you a little bit about how the Atlas platform works, and this is a very much speeded up video, but I just want to show you some of the features that make it accessible to our student cohort. The first thing, if we focus on the left-hand side of the screen, is that all of the videos are closed captioned. So for many of our students, they're working in English as a second language, and having the closed captioning can be very useful to them. The other thing that you'll notice is the dynamic reasoning graph here on the right-hand side of the screen. And you'll see that as the different concepts come up on the slides, they're reflected in the dynamic reasoning graph. So the students have an overall sense of what the lecture is about and how all of the parts come together. And as I said, each of those nodes inside the dynamic reasoning graph can actually have additional information included. We can embed in the video formative tests. So you just saw a formative test come up there, a formative question. So you can insert 1, 2, 3, 4, as many of these formative questions inside the video as you wish to have, so that students can check, have I really understood this program, this idea or not? Do I know how to apply what I've just learned, or have I learned it sufficiently? So at least for us, we don't actually grade those formative assessments, but we do use them later for the summative assessments, and they provide a guide to that. The other thing to be said here is that underneath the slide, we can have all of the content that we want there in terms of papers, lecture notes, and so forth. that the students will need. We can also, we also have in here a chat. We find that peer-to-peer learning is extremely important, and allowing the students to speak to each other is a key part to accelerating the learning process. So just to take it one step further, of course, we started talking about, the boron trichloride. Then, we talked to the students about expanding that to three-dimensional space. And these are just the simple ideas about Pauling's rules, making sure that, you create stable polyhedra, and this idea of structural eutaxy. So again, this tends not to be new to the students. They have met these concepts before. But we identify again, what is the driver? What is the function? What is the symmetry? So we link those very carefully together so the students understand the relationship between them. And then this is where things do tend to get more complicated for some students. Most students have learned at some time about, of course, describing crystal structures as spheres, where you have sphere packing going on and you look at the size of the interstices and so forth. But again, if you think about battery materials, these sorts of representations don't help very much. You really have to think about the polyhedra and take the representation shown on the right, where the polyhedral shape is considered as the unit, often the invariant unit. So you're looking at longer range order before amongst those invariant units. And then this is where we start to get into the practical part of the teaching. So we make a lot of use of precision polyhedra and have the students actually build structures in their own right. The starting point, however, is that they understand what polyhedra are. And many courses, of course, begin with the Platonic solids. But what we want to do here is not just look at a shape and say, that's a tetrahedron, that's an octahedron, that doesn't work. We should be able to allow the students the opportunity to understand deeply the difference between these, and the fact that if you've got something small like a tetrahedron, you really only can fit 4 nodes around it, or 4 vertices. And we can link the building of the polyhedra, as is being shown in this video, to the underlying crystal chemistry, which favors one polyhedra over another. You can also see a lot of information around these videos about the Cartesian coordinates, the fractional coordinates. And this is very important because if you look at the end of each polyhedra being built, they not only build the polyhedra, they have to be able to calculate the polyhedra and do a perfect match. The capacity to use various softwares to calculate and match polyhedra forces a discipline on the learning the students don't usually get. And of course, looking at different polyhedra is the basis, particularly of many spectroscopies, where you want to calculate the spectra, Raman spectroscopy and so forth, where you want to calculate what the spectra will look like. You cannot calculate those spectra unless you understand about polyhedral shapes and point symmetry. So this is another way that we do it. And usually the students really love building these models because it gives students some physical form to what they're learning. And whilst we can do a lot with online, methods and tools to plot, having something in your hand can be very important for many students. Now, the next thing I'd like to look at briefly is the question of assessment. And so in the Atlas system, we have multiple choice question sets, and you'll see in a moment we also have essays. But the multiple choice questions, as you can see, they can be quite intricate. They can include figures. There can be more than one correct answer. We can also have answers which are actually short sentences, which can be checked against and so forth. But you can see what's happening here. The beginning of these questions are more things like everyday objects and tessellations that come from Escher, and then gradually move towards more crystal chemical descriptions of structures. So these types of tests can become quite intricate. They might require some calculation to arrive at the right answer, or They might require looking up databases, for example, a Bilbao crystallographic server to get out information about three-dimensional space groups. They might require looking up crystal databases and learning how to read those databases correctly. So typically, this is a set of 10 questions. We usually give our students an hour to answer these questions because, for many students, it's not just a simple, I can guess what the answer is. They really have to do some work on the internet to extract back the information they need to answer these questions. We also include essays in this type of course. And I'm personally a great believer in authentic texts. So even the undergraduate students have to look at scientific papers. And you can create very well-defined rubrics that ensure that the students can write essays against this carefully constructed rubric. But more to the point, we have our students mark other students' essays. Because in my experience, even if a student can't write a good essay themselves, they recognize it when they see it. Similarly, the good students can see how other students have struggled or see how other good students have approached a question. And here at the bottom of this pull down, you can see where we've set up how the students should write the essay. It's very constrained in terms of number of words, but also very directed in terms of these are the concepts, these are the ideas you must demonstrate an understanding of. So again, we let the students work at home because they're working against authentic texts. It's not really possible to cheat in an absolute sense, but of course we do encourage the students to work together as teams. I also add that this platform has a plagiarism checker, and unless the writing is 90% original, they simply can't upload the essay. So that allows us to have quite a bit of scalability in this. Just in terms of some of the analytics as we go along, on the left-hand side of this slide, you can see that I can monitor the progress of students undertaking the course and make sure that they're not falling behind. So this has proved to be exceptionally valuable. I can see immediately students who have some problem, who are struggling and are not coping with the course, and we can identify them very early. And if we go in deeper, you can see I can view which lectures they've undertaken. I can also look at what assignments and questions they've already completed. On the right-hand side, I've got an example of where we have peer marking. And so for the essays here, every essay is peer marked by 3 other students. Inevitably, there's a little bit of moderation at the end, but by marking against that carefully constructed rubric, the students really tend to come up with fairly even marking of their cohort. Now, the last thing I'd like to deal with is the idea of laboratory practice and coming back to this physical model building. And what I've seen over the years is that, there's numerous programs where you can plot a crystal structure, but often that leads to very little understanding of what is going on within that structure. Sometimes the programs get too clever and they will, generate their own polyhedra, which might not be the appropriate polyhedra for a particular type of structure. And the students actually struggle to take a computed representation and build the model often. You would think it's not that difficult, but bringing together the hands and the head to do these exercises is not easy. And it also forces the students to slow down and reflect upon what they're learning. They cannot rush this exercise where they have to build a model. The other thing is that, and I mentioned this right at the beginning, it's very good to have a basis for what is the perfect structure, what is often the close-packed structure. How do you describe the close-packed structure, and what are the departures from that, and what basically drives those departures? This is also important. And finally, we expect the students to build a structure. I'll show you an example in a moment. Build a structure, take a photograph, and calculate a representation which is identical. And again, It's forcing the students to slow down and reflect upon what they're learning. So in this particular slide, I'm just showing you a calculated representation, a physical model for an intergross of sphalerite and wurtzite, but obviously you can do anything. So this is just a training video that we use for the students. This is looking at structures containing two types of polyhedron. I thought I'd just take the example of perovskite, which so many of us are familiar with, but your basic cubic perovskite, of course, is cube octahedra and octahedra, and this is just showing how students can construct these. But surrounding the construction video, you can see a lot of information, and depending on the level of the students, you can take more or less of that information and expand upon it. So of course they have basic information about space groups. They should be able to go to the databases, extract this information and understand what is there. They need to understand about special and general positions, because later on, if they start to simulate X-ray patterns, spectra, and so forth, if they don't understand the difference, they're likely to end up with the wrong result. They can start to think about the bond lengths, and they can obviously see the TiO bond length is shorter than SRO. So what a surprise, titanium is in the smaller polyhedron, tetrahedron, the octahedron, and the strontium is in the cube octahedron, and so forth. And so this goes along, and they can construct these models, thinking about the structure all the time. And at the end, they need to be able to calculate, have a computed representation, which is exactly the same as the model that they built. So this proves to be a very powerful learning tool. I've already mentioned about the fact that you need a basis for comparing structure. What is the real structure versus the ideal structure? And again, I won't go into any detail here. It's not necessary for this group. But this is an example of the question that was in a semester that just ended at NTU, where they had to build this barium ruthenium oxide, which is a mixed hexagonal and cubic close-packed perovskite. But you can see that on one side, they were given the real structure, and on the left-hand side, they had to figure out what were the ideal coordinates. So immediately then they can calculate metal-oxygen bond distances, and they can see what is going on. And of course, once you have the ideal structure, then the metal-oxygen bond distances must be all the same. So there's kind of a self-checking in there. They can get a sense of satisfaction that they've obtained the right answer. And this is just an example of a model and computed representation that one of the students presented for their assignment a couple of weeks ago. So this is a very complicated structure in some respects, but then they went beyond this and they looked at the hybrid perovskites, which have the same framework. So once you introduce hybrid, the organic component, the structures look incredibly complicated. But if they start with the pure inorganic version and then look at the hybrid analog, it makes things much clearer. And again, you can build a degree of complexity around this depending on the level of the students that you're teaching. So finally, I'll draw this to a close. One of the things that we're very concerned about, particularly in these days of using artificial intelligence, machine learning, all of these things to try and accelerate materials design, is that you still need a fundamental understanding of symmetry and a fundamental understanding of crystal chemistry to know if what's coming out at you makes a lot of sense. And I think many of us involved in this field have seen things which are absolutely, first rate from these machine learning approaches, but other things which simply make no sense at all. And so we hope that the students go away having a sense of what is appropriate. And of course, if you want to simulate spectra, if you want to simulate microscope images, which are essentially plain cross sections, whether it be AFM or TEM, you need to understand the symmetry so that, it's not rubbish in, rubbish out. You put in the correct information. Of course, the same is true for crystallography. So this is where we want to get to. We don't want the students to be crystallographers in any sense of the word, but we want to have them have an intuitive feel for what will make sense. And so finally, just to bring this to a close, these are a summary of what we have discovered, which is basically that having that dynamic representation or knowledge trees of the entire lecture, showing how all the major concepts are connected to each other, is really very helpful for the students. We make extensive use integrating this with chat sessions, synchronous tutorials and so forth, and particularly peer-to-peer interactions, which also serves to accelerate the learning. And then we have these variety of assessment options, but we don't use multiple choice very much. We rely very much on essay style questions because they can reflect a deeper understanding. Although, as we know, artificial intelligence can now write some very good essays on science themselves. So I do feel that in the future, we're going to have to be very careful how we design these questions. And finally, as you've seen, we were able to integrate a practical component within the course, which was the model building, but we could equally well extend that through to Rietveld analysis of X-rays, high resolution TEM computations, and we have done this in the past, but this provides a basis for that type of study. So very briefly, that's an overview of the ways in which we're accelerating learning here. And as I said, it's all about, as Raman said in his quote, you know, it's about asking the right questions. So we want students not necessarily to know everything, but understand where to go to get the information they need and formulate the questions in the right way. So I think I will stop there. I've used up my time, I believe, but I'm happy to take any questions now or at another time. So thank you very much for your attention.